Hello and welcome to some C4 revision
The final leg.
of the struggling prisoner that is an A-level maths student.
I think, yeah, prisoner's a very good term.
I'm Will Carne.
And I'm still Carne DURKIN.
And welcome to part A of Wahey Productions Maths Revision Series.
C4.
This video is all you need to know for an A star, but if you have any questions, you're welcome to ask in the comments.
Onwards!
Let's begin with partial fractions, the easy bit with which everyone thinks should be in C3.
It really should, it's quite nice. I like it.
Go for it.
Given a fraction, like so, you can simplify the nasty looking fraction by turning it into partial fractions.
So begin by factorising the fraction and then write out what you're aiming for, with constants to be found A, B, and sometimes C.
Ooh, C's a good one. Then multiply the whole equation by the denominator, so in this case by ax plus b, cx plus d, and ex plus f.
This will get it all on one line and ready for some sneaky algebraic manipulation. Then pick a value for x, which will make two of the three brackets 0. So in this case, minus b over a, which will eliminate the blue bracket, therefore making those terms 0.
Then you can solve to find a.
Yep. Then sub in a different value and so on. This will get you a, b, and c, known as the method of substitution.
Dun, 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 dun.
If one of the denominators is a degree of two or more, then you need more than one partial fraction. So in this case, you have two partial fractions. You have one that's got for example, ax plus b squared, and the other one that's just ax plus b. If that makes sense. It's basically, if you were to multiply those two together, then you would only have to multiply a over ax plus b by ax plus b to get two like fractions. That's where it comes from. I hope you sort of get that.
That's where babies come from.
So if the fraction is an improper fraction, then so the top's bigger than the bottom, then you
In
need
terms of power
to
of x.
faff around.
Faffing. You should be able to tell this by the highest degree of x. In this case, you'll have to expand the bottom so you can divide it algebraically. This, just like C3, will get you an answer and a remainder.
Then you can make partial fractions out of the remainder, and so you just add on your dividing answer at the end.
Just remember that your remainder is over your original denominator, but you'd already know that for C3.
Yeah, we made that pretty clear.
Wow.
Now, you've been using Cartesian equations for most of your life, but it's time to get the mistress or a toy boy, which are parametric equations.
These are where you have x and y in terms of some other variable or parameter.
You see where that comes?
Parametric?
Yeah,
Parametric?
there are three things that you need to know about
Three, sir.
intersection, differentiation, and integration.
Well, I know two of them, so it's all good.
For intersection, it is when all the variables are the same. So the easiest way is to usually rearrange it for t, then equate to get a Cartesian equation. Really?
All shown by this lovely example.
Oh, isn't that lovely? On to differentiation. Oh, sorry. Or you could do another form of substitution as shown. It depends how complicated the equations are, really.
On to differentiation. Even I can't speak today. Now, some rearrange it into a Cartesian and go how they know, which is, simple. But the best way is to differentiate such equation in terms of t.
Then by dividing one by another, and the third variable will cancel out, giving dy by dx. So, I'll give you an example because you look very confused.
I do look very confused.
Yes. So you just divide dy, you do dy by dt. You differentiate the y1 to get dy by dt. You differentiate the x equation to get dx by dt. And then if you do dy by dt divided by dx by dt, then it's dy by dt times dt by dx, as dt's cancel out, and you get dy by dx.
This seems very complicated.
It looks simple. Look, doesn't that look simple?
It looks simpler there.
It does.
Look at it.
Or you could just rearrange it into a Cartesian equation and do it normally. But then that takes a lot longer. Now on to integration and another trick. Now taking the usual, which is just integrate f of x between b and a. Yeah?
B and a.
Yeah.
B and a.
You can integrate the y equation in terms of t multiplied by the x equation differentiated.
It works. As you can see, the dt will cancel out, leaving an integral of y dx, which is a normal integral.
Yeah, because we said all the way back in C1 that you put dx on the end, and this is why, because you're integrating with respect to x.
Much respect.
Or you're
so you get the new limits in terms of t, sub in the original limits into the original xt equation.
Now I've been using t as a parameter, but it may be theta, using trigonometry I'm afraid, or it could just be any other third parameter, but I like using t. I don't know why.
T is a good letter.
It is. Yeah, it stands for towel.
That's That's so deep. I can't. Oh,
Right.
the feel.
Binomial series.
Do you remember this torture from C2? You should do. You really should. Maybe some of you are doing C2.
But don't worry, because in C4, binomial series is completed and hopefully finally makes complete sense.
Da, 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 da. Okay, so in the formula booklet, to recap, this first formula is the full formula for any binomial expansion, giving the expansion for any parameters or variables. The second formula finds the coefficients manually using either a calculator or the factorial long way round.
The last formula seems to be a special case, but it can be used every time using a trick, which I'll show you a little bit later. That's essentially the whole of C4. The important thing about this last formula in C4 is that you can only use this one when expanding binomially where n is negative or a fraction, or knowing my luck, both.
A negative fraction. Now, in a normal expansion of it, like so, the powers of the variable increase by 1 and the coefficients can be found using this or Pascal's triangle. But with negatives or fractions, that falls apart completely.
So when you have an example, like 1 over root 3 plus 2x, which becomes 3 plus 2x to the power of minus a half, see, it's both, which is sad, then you can write it, well, that's written ready to expand it binomially. The trick is to factorise it, so that you are left with 1 plus something, and then you could use that third little formulae, and use the factorial formulae as well. Because your calculator and Pascal's triangle break down here.
Break down
when it gets
worse
there.
than a Dutch dam made out of Swiss cheese.
Just remember to multiply the power by whatever you have taken out the front, basically, and at the end multiply your answer by it. So in this case, the expansion will be 3 to the power of minus a half multiplied by 1 plus 2/3 x to the power of minus a half. See what you've done? So you've got it into 1 plus something sort of bit, which you can now use to expand using the original formula.
Ah, very clever.
Isn't that clever?
Yeah.
And you've also now got it ready so you can use the n factorial over r factorial blah, 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 to find the coefficients. So, expanding it, you get all multiplied by 3 to the power of minus a half. You get 1 minus a half times 2/3 x to the 1 plus 3/8 multiplied by 2/3 x squared minus the 15. Yeah, you can see. Can you see where this is going?
I see many
Can you
things.
see where all this is going?
Can you see the light?
In these cases, the formula will expand forever, getting closer and closer to an answer. Sort of, if you know what I mean. As you can see, you can sort of see why. As the negative values, when squared, become positive, and then otherwise they're negative. So it sort of goes positive, negative, positive, negative, positive, negative, getting smaller and smaller and smaller and smaller. So you can see how that gets closer to a value. You can see how Connor's gone quiet because he's got no idea what I'm talking about.
Yeah.
Yes.
I'm just thinking about ducks.
And with fractions, you can just go smaller and smaller and smaller, really.
Like
If you're confused, that is essentially why you have to use this method for infinite expansion. Yeah.
Not to be confused with very long expansions, like to the power of 20.
Yeah, so if it's a binomial expansion to the power of 20, it'll be really long, but you could finish it. Whereas if you have these, some of them are just infinite. They just go on forever because it's, yeah, you see what I mean?
This is evil.
And that's why you can't have a Pascal's triangle of it, because it's infinite. So you couldn't ever get a line that would be
Long enough.
Yeah.
Okay.
See,
then.
that's why it all works out.
It does.
Right, so usually they will ask for expansions up to the x cubed term, probably, which means you just stop when you get to whatever they ask, really.
They may couple this up with with partial fractions or some other thing, etc., in which our advice is to possible overkill on the expansion. What?
Yeah, just overkill in the expansion,
Oh,
and
right.
then only write your final answer up to the degree of x they want.
Oh, my bad.
So just expand possibly to another degree above what they want, and then just add your final answer, only tell them up to what they want.
They may also ask you for an approximation question, where you approximate an answer like 0.999 to the power of 8.
Yes, by using 1 minus x to the power of 8, and then you can expand it a little bit, and then sub in x equals 0.001, and then as you can probably see, that will give you an approximation to the answer of that without using a calculator. Well, you probably will need a calculator in that case, but that's not the point. You sort of see what I mean. And as it goes infinitely on, the more terms you have, the closer your answer will be to the actual correct answer. So you can use it for approximating things. That's what I'm trying to get at. I hope you can see why it works. If not, ask below and I'll happily explain, but I'm assuming you do. Or yeah, okay. Let's move on. Connor wants to move on.
I really
To
do.
differentiation.
You thought it was all over in C3, but there is more, Mr. Bond. And there's actually some more in the next video, but that's a by the by. Let's just get going with a handy skill that is implicit differentiation.
This is where you attempt to differentiate something with respect to something else. So differentiate y to the n with respect to x. You get n multiplied by y to the n minus 1 dy over dx. A nice way to think about it, perhaps, is that it doesn't work. So it's a little note for you to sort it out later, because it's differentiated anyway. Because you don't care what people think. You're your own person.
We're a strong, independent... Okay, moving on. So x cubed y squared can now be differentiated using implicit and the product rule. William?
Yes? What? I don't know where we are.
Neither do I.
Oh, yes, right. So, yeah, it becomes 3x squared y squared plus x cubed 2y dy over dx. You see the product rule, the implicit rule is why there's still a dy over dx in it, and the product rule is why it's been split into the thing. Okay? Clear?
That's crystal.
Right. And the classic x squared y, which is kind of one you should be able to recognise, is 2xy plus x squared dy over dx. Now, if you're given something like this, which you will be, it's a classic example of a need for implicit.
Here you differentiate like so, and then solve to get dy over dx on one side, and that is your differential. Sorry.
Yes.
Simple, really.
So, yes, so it's essentially you start... It's getting a little bit tricky, but as long as you get the concept of what dy over dx is, or it might not be that, it might be something else, then it's really easy. It's just rearranging. And it's just another sort of variable, if that makes sense.
Simple.
Does it make sense?
Simple not to say.
Right.
Yeah,
I personally think it's my favourite area of the A-level, because this alone explains why all the little things in differentiation and later in integration work. It does. Trust me, I'll show you in a minute. With parametric equations, I will remind you of the trick. There it is. It's dy over dt divided by dx over dt.
I remember this,
and the
yeah,
dt's cancel out. You remember this one. So yeah, I told you about that earlier, so I won't tell you again. Finally, a reminder from C3, the differential of a to the x, which is a to the x ln a.
E is a special case because natural log e is just 1, as ln is log base e. That's why e to the x differentiated is just e to the x. That's so clever. Scary clever. But you need to know this, especially when you're doing growth and decay. You'll have something looking like this, where t stands for time, the graph with a positive value of t will be exponential growth, the graph with negative will be exponential decay. A is the value where it goes through the y-axis, or sometimes its starting value, found when x is 0. You may need your indices laws, like this example.
There we are. See that? See your indices law? See, you're separating it. So e to the power of 2t plus 3 becomes e to the 2t times e to the 3. Carry on.
Rates of change, usually of populations over time, can be found to the differential... Oh my god, I can't pronounce that. dp over dt.
This is where you won't like differential equations. Next video. This is where this is all. Yeah, this is all in the next video. This is what the script says. I'm just preparing you to detach yourself from your clingy nature to x and y.
But I love them.
I'm sorry. It's time to see some other people. It's not me. It's you.
Oh.
That's it for part A. Join me next time for some differential equations. For some what, Connor?
Differential equations, differentiation.
Vectors and the trig of C4. That is integration. Sorry, that didn't really make any sense. I've been Will Carne.
I think you'll find what actually is integration.
I've been Will Carne. I'm sorry if this video has been a bit hickledy-pickledy.
And I've been Connor Durkin, very confused and glazed.
You've been watching Wahey Productive Revision material. If you've got any questions or queries, and I understand why you might do on this video, please ask in the not in the description, in the comments.
He will answer them.
Oh my god, sorry, this has gone a little bit out the window, this video. Will be all clean and better by next video. See you then.
Bye.
Oh god.
I'm being held against my will.